Hello friends and welcome back to C for You. Today's video is about Kolbe's reaction. We'll see the reaction, mechanism, products, and as well we'll solve some problems. Okay. So actually the Kolbe's reaction is a special kind of reaction which takes place with the phenols. As we all know, phenols cannot react itself. So first it's needed to convert. So it is phenol, and phenol is needed to be converted into the reactive species. That reactive species we made it by treating phenol with NaOH. So what does NaOH do? NaOH is a base, looks for acidic proton. Phenol has an acidic proton, which is this one. So it abstracts that thing and will give you ONA. This is what we call as a sodium phenoxide, and sodium phenoxide is very much active species. Okay, it's a nucleophilic in nature. Sorry, it's being somewhat conjuncted, but doesn't matter. And now what the next step is, it reacts with first CO2 and then with acidification gives you a special kind of a product which is known as, I guess you guys know the name of this compound. This is a very much important compound in the organic chemistry, nothing but the salicylic acid. That much simple is the preparation of salicylic acid from phenol. Yeah, so this is for the reaction, this is for the Kolbe's reaction. Now we'll go for its mechanism. Let's go. How mechanism goes. Okay, yeah. So first thing what we know we have to do is take phenol. Here is your phenol, OH, NaOH, go with NaOH. Yeah, it's plus, it's minus, so it will take your proton and will make it as a O minus, which we can write with a sodium as a counter ion, which we will call it as a, yeah, sodium phenoxide we are with. Now see the difference. And yeah, one more thing, in the salicylic acid something is going to attack on CO2. Yeah, if it's going to the ortho position, then it's a possibility of COOH to go to the para position, but this reaction is the ortho directing, hence ortho product is a major product. The reason I'll tell you at the last of this video. So now let's continue to the mechanism, and I'll just change the position of these double bonds for the convenience. Okay, so now what we have C double bond O, C double bond O. With conjugation or with resonance, these bonds opens up on the carbon. This carbon is very much electrophilic. The reason is two oxygens besides it, and rather more CO2 is acidic. You must know it. Yeah, so it will open here. Now we are getting O double bond. One might be thinking of sodium, so guys, it's a counter ion. It's being stabilized in the solvent. Yeah, so up to this it's okay now. But guys, you can see the aromaticity of the phenyl ring or the aromatic ring is vanished. So what happens, this is what the special case, and this is what the very much important thing which takes place in all of the electrophilic substitution or nucleophilic substitution, which we call as the re-aromatization. To know this concept, you can go to my last videos, they have explained the same. And what happens, it goes here and the bond goes back. In many of the books or in many of the reactions, you may see this hydrogen is taken by this O minus and then it goes up. You can show that doesn't matter, because after all, when this hydrogen gets free into the solvent, it's being abstracted by the same anion. So it doesn't matter if you show in the same step, and what you are getting is C double bond OOH and the aromatic ring. Yeah, and then here is the last step, your reaction, acidification. because you have this oxide ion that has to be stabilized, that has to be acidified, protonated, because in the first step you took up its proton, no? So here is now the time to return it, and this is your product. This is what the salicylic acid. Yeah, so this is for the simplest Kolbes reaction. Now yeah, we'll go for the problem. So friends, here we have some problems. So first you're with alpha naphthol, then yeah, it's cresol, then dimethoxyphenol, and what's it? It's anisole. Okay, fine. The first problem, I think everyone can solve it, because at this position you are going to get COOH in this manner. So here is OH. I don't think there is need to explain the mechanism. If you didn't get the mechanism, go back to the video, watch the mechanism again. I hope it's much easier to understand, and it's explained in the easiest way as I can. Yeah, so the second thing, you are with cresol. Yeah, in this case also again you'll get ortho product only, OHCH3. Yeah, the reason of getting ortho product, it's yet to be explained. Yeah, I'll go for that here. Okay, now see, both of the ortho positions are blocked here. There is possibility of the reaction to perform, but it's very less possibility, and you're getting this product only there. Of course, this is only the possibility remains, and here we'll go for this one first. See, you don't have any proton over the oxygen, so there is nothing to create nucleophilicity in this reaction, so the reaction doesn't go. You must have a phenol only. Okay, this is the question from I think 12th standard question paper, that whether it will undergo Kolbes reaction or not, doesn't matter. Yeah, so at the last we'll go for the ortho selectivity. So here are the two possibilities of the salicylic acid to be formed: ortho and para salicylic acid, means I mean ortho hydroxy benzoic acid or para hydroxy benzoic acid. So the reason of being ortho as a major product is this thing, the hydrogen bonding. Yeah, which is not possible here, over here. So for that sake only, ortho product becomes major one. That doesn't mean there is 0% formation of this thing. Yeah, there is something formation, but it's negligible, hence we write only single product. So guys, this is about today's video, and in the next video I'll come up with Navier reaction. Till then, just enjoy the chemistry, stay home, stay safe, enjoy the lockdown. Thanks for watching the video.